as well.
Okay, good. Okay, welcome everyone. So look, just the remit of this talk is a short synopsis of the role that genomics can play in breeding programs, and obviously tailored towards the Angus breed in this case. So look, this is a slide that Professor Aberdeen-Angus often uses to try and explain, you know, the impact of DNA and the relationship. So, you know, he indicates that we all share 99% of our DNA in common. We share 98% with primates, 84% with canines. And on a light-hearted side, you might be able to see some spurious similarities between Dunnes specimens. So look, whether you see them or not, they're obviously Dunnes can see something in them. So anyway, look, the same DNA profile exists in all the cells of our body, almost all the cells, with the exception of some of the sex-related chromosomes. And the DNA that you're born with is the DNA that you die with. And each cell contains somewhere in the region of 3 billion pieces of DNA information. And I suppose, look, in summary, DNA has many uses, which we'll try and cover a few of these today. So in the context of we'll say, you know, cattle breeding or sheep breeding or domestic livestock breeding, you can see there's a whole range of areas listed there, and probably we were touching the surface of what genomics can do, genotyping can do, and really it's around the first couple of areas here around parentage, assignment and discovery, but also in terms of the increasing the accuracy of genetic/genomic evaluations. But there are a whole range of other areas there. We're obviously touching on some of the genes, the major genes that are impacting the Angus breed, such as myostatin, but also there's a role for DNA traceability, detecting lethal genes, deriving breed composition, monitoring inbreeding, mating advice, and sex determination. So we'll cover some of these, but obviously some of them then will be covered later on by Katie. So we'll just cover some of the bigger areas. So the first one I'm just going to cover is the area of parentage assignment and discovery, and linked to that is the sex determination. So ICBF are active members of ICAR, which is the International Committee for Animal Recording, and it's a global organization. Some of you may have heard of it. Its core remit is to develop products and services such as guidelines for evaluations, certification services. They organize seminars and workshops on 4 key areas around animal identification, recording, evaluation, and management. Okay, so they have a far-reaching impact in many countries, and some may have heard of the Interbull Centre and the Interbeef services on the back of that. They are actually subcommittees of ICAR. So ICAR is the local body. So with regard to parentage assignment and discovery, ICAR have a working group around parentage, and as part of that group, they have an internationally agreed parentage panel of around 800 SNPs. Okay, so and 200 of those are what we call, which are ICIG SNPs, which is another international organization, but also 500 are new SNPs which ICAR has identified, and between them there, and there's an extra 100 SNPs on there as well. They're what's been rolled out now as the agreed parentage panel from which countries that are agreed to sign up to the ICAR parentage service will use. Okay, so there's regular validation and reaccreditation, and you can see on the right hand side there, this is ICBF's current accreditation logo. So you can see there it's due to expire in October 2022, at which point we'll have done tests and we'll get our license for that service for the next couple of years again. Okay, so again it continually evolves. If some SNPs are underperforming, they tend to be moved out and some new ones brought in, but by and large that's quite a stable parentage panel at this stage. Okay, so ICBF run that parentage process weekly for any new genotypes that have come in, and it runs parentage assignment and also parentage discovery. As part of that then, there is a sex determination there. So in a small proportion of cases, a sex might have been recorded wrongly by a breeder, or there is a small proportion of these that are affected by what's called a Turner syndrome, which they look to be female, but they actually have two X and a Y, and basically they tend to turn up as be indicated as males based on the genotype. So look, the main one here really is the parentage assignment and discovery with obviously additional confirmation on the sex. So I know Felicity and Siobhan had mentioned the number of genotypes that were in the database. So this is just some recent stats that we pulled around some of the metrics around the current parentage verification process. So there's about 2.4 million animals, commercial animals that have gone through the pipeline, in addition to about 426,000 pedigree animals. And just some of the metrics on those, of that 2.4 million commercial animals, at this stage, about 77% of those actually have a sire genotype as well. In the pedigree, it's slightly higher. It's about 88% of them. And in terms of sire to offspring conflicts that we are seeing, there's about 17% what we would say is wrongly recorded sires. Basically, it's not far off 1 in 5. And you can see that 6% on the pedigree side, so still a significant amount on the pedigree side of parentage errors. In cases where the predicted sire is unknown, or where a wrong sire has been taken off, we can predict a sire in 8% of cases on the commercial side, and in 1% of cases on the pedigree side. In the context of genotype dams, you can see about 62% of the commercial genotypes actually have a dam genotype as well, and 53% of the pedigree. I suppose in the context of the 62% here, they're mainly based on cows that were part of the beef data and genomics program, where farmers were incentivized to genotype their cows in order to reach certain targets. So also in that case, you can see that 6% there was 6% of dam to offspring conflicts, and 2% in the case of the pedigree cows. So it's just some high level stats on the parentage process. So the next area we're going to cover was the use of genomics to increase the accuracy of genetic evaluations. Okay, and some of this probably was covered by Siobhan, but it's no harm to reinforce it. We talk about a number of key pillars that are needed to drive genetic selection. Okay, so and specifically in this case, it's driving profit through genetic selection. So the first one then is the ability to have an integrated database recording all the information that's available in the industry. The second one then is having an agreed breeding goal and a subsequent selection index that will help you achieve that breeding goal on the back of that. And there's two components to that. One is the genetic evaluations, which can give the strengths and the weaknesses on an individual animal for a whole range of traits. And the second one then is the bioeconomic models that Siobhan has mentioned. And they are combined then into a selection index. And just put in two examples here, the replacement index and the dairy beef index in the context of the Angus and indeed all beef breeds. Now the third component here is then to have a working breeding program that will identify the best animals and use those to produce the next generation. Okay, and you can see there's two aspects here. There's a maternal beef breeding program, which is specifically designed towards the sires that are going to produce the cows of the next cows in the beef herd or suckler herd, but also the next generation of dairy beef sires to be used on dairy cows. So two slightly different programs. Some bulls will obviously suit both, but they're targeted slightly differently. Now, adding on to that, then, this is just another way of looking at it in terms of key components of actually genetic gain. Okay, and there's a well-known formula there that is used to try and describe this. Okay, so and there's four components here. The first one is the genetic variability. So there's no point in trying to breed for something where there is no genetic variability. I think Siobhan covered that with her example of the hen versus the variation in height. And if you look at within the the Angus breed in Ireland, we can see that there's a standard deviation of €40 between the best, well, not necessarily between the, it means that it's a measure of the variation that exists in the Angus herd for the dairy beef index. Okay, so there is genetic variation there for that index, and you can actually breed for it. The second one then is the accuracy of selection. Okay, so how well are the candidates that you initially select to be the parents of the next generation, how accurate are they, and how likely are they to change over time? And just to explain, what I have here is basically on the x-axis here, I have the reliability. As you can see, it's going from 0% up to almost 99%. And what I have here on the y-axis then is the likelihood of that index to change when that animal goes from this point to when it's fully proven. And you can see then that if you had no genomics and you just had a parental average, we'll say for the replacement index, and it sits there at about 17 or 18% reliability, there's a big opportunity for that individual index to move. Okay, and number one, it could move based on the wrong pedigree being recorded. Number two, could be based on very little data known about that animal in the system, and that parental average is not very reliable. So then the next shift on then is where potentially you have both parents with a genotype and a genomic breeding value on them. So the level of risk around movement reduces slightly. Then you move on to where you get the actual animal genotype itself. That brings down the risk. And again, it's only a hypothetical example here, but it will be a similar case for all traits. And finally then, so you have a genomic evaluation on that animal, but as you genotype more and more animals in the population and more informative animals come in, that's what's called your reference population. That gets better over time and it gets more accurate. And again, that squeezes down the likelihood of that individual animal's index moving. And finally, then you get up here to a small proportion of animals that are almost 99% proven. Okay, they still have a capacity to move a little bit, but not near as much. So they'll move very, very little, as huge volumes of additional data come in on them or their relatives. So that's the accuracy of selection piece. And what we have seen across the traits is that on average we can see somewhere in the region of about 36% increase in accuracy as we push genomics into the system. So that's always good, and it is getting better as the reference populations increase over time. The third measure that here we talk about is the intensity of selection. So it's how far you pick the best animals, and they then drive on the population. So if you look at the top 1% of the Irish Angus animals on dairy beef index, it's up around €195. So that will pitch them up here where the cursor is. Okay, so that they're really at the very top end. So if you can end up with a panel of bulls based on that value, you'll make more progress than, say, if you pick a panel of bulls that are representative of the top 20 or 30%. So the final component of this is the generation interval. It's the gap between the average age of the parents and the average age of the progeny. And currently, in the context of the Angus and pedigree Angus in Ireland, it's about 5.1 years. So that's the average of the mother and the dam compared to that's the average age of the mother and dam when the calf is born. Now, obviously things are moving a little bit slower on the beef side, but if you take that into consideration on the dairy side, the average dairy sire now is probably somewhere between 2 years and 2.5 years when the calf is born. And the dam is obviously slightly older, but the generation interval, as we know, the adoption of genomics in the dairy herd has increased at a rate of knots worldwide. So it's not directly comparable to the beef, but it just shows you the capacity there to bring down the generation interval as a key component to improve genetic gain. So another key component to the use of genotypes is in the context of foreign genetics. Okay, and I'm sure every country is the same. A lot of countries represented here tonight, but if you look at the Irish Angus population in 2021, 5% of the total Angus population of about 250,000 calves born were sired by foreign sires. But if you just look at the pedigree Angus population, it was almost 1 in 5 were sired by a foreign sire. So obviously, Irish breeders are very, I suppose, active in securing outcross sires and using those sires to breed the next generation. So it's important to try and put as good an initial prediction on those sires as possible. I suppose there's kind of 2 key areas that we try and improve that initial prediction. The first 2 are around integration of international or foreign EBVs. And when I talk about international EBVs, it's the participation in the interbeef evaluation that's run out of the Interpol Centre, where we get back, EBVs for a range of traits around Charolais, Limousin, Simmental, and the Angus and Hereford are actually in development as well. So they should come in future. And you can just see the some of the countries that are represented in colour down here, mainly Europe, but starting to collaborate now with let's say Australia and New Zealand. Also, we have a two-way sharing of EBVs with some countries specific evaluations, such as the IBOVAL indexes for the French breeds coming from France, but also in the context of UK breed plan for Charolais, Simmental, Angus and Hereford. So we would send over routinely a list of animals that have been we have found, let's say UK animals we found in the Irish pedigree, and we'd request an updated set of EBVs on those. And we also get UK Limousin, which are not part of breed plan, but they have their own evaluation, which is run out of the Scottish Rural Agricultural College, who compute their evaluations. The other component we do is for any AI sire that's passed for use in Ireland, they have to have a genotype, what we call a valid genotype, a genotype that has passed all the checks. So there's 2 aims to that: is to make sure that the parentage is right, but also to allow to get an initial early prediction on genetic merit. Okay, so that either comes in the form of the collaborating organization sending the actual genotype if they have the animal done, or sending a DNA sample from which we can actually generate a genotype for. So this is a slide just to indicate the impact of those 2 measures on foreign sires that are being used in the Irish breeding program. Okay, so there are sires here which have no Irish progeny in the evaluations, but they're in the ICBF database. And I've just 2 categories here on the left hand side. You can see whether the animal has the genotype or not, and whether the animal has a foreign EBV for any given trait or not. Okay, so when you see the first category of animals where they don't have a genotype, or they don't have a foreign EBV to integrate, about 385 animals in that category, you can see the reliabilities are low. Okay, we don't have a whole lot to go on these animals. So basically the average reliability is only 10% for terminal replacement and 9% for DBI. Okay, in the context of the next category, where we still don't have a genotype, but we have a foreign EBV, you can see that the reliabilities are increasing. So you're getting a little bit more information into the system by virtue of integrating the foreign EBVs. The third category then is where you have a genotype, but you don't have a foreign EBV, and you can see there's 271 animals in that category, and they're actually a little bit more reliable. So what it is saying is that, yeah, that genotype is quite important, and even a little bit more important to increase the reliability than the foreign EBV in some cases. And finally, the category that you can have most confidence in is that category where they have a genotype, they have a foreign EBV. There's 55 animals in that category. You can see that the reliability there is 46%, 42 and 45. So it's quite a step up from what we know about these animals up here, which have neither a genotype or a foreign EBV available. It also has a ripple effect into the actual initial value that gets put on these animals. So you can see that here that the initial, let's say, terminal index on this lower group here is 90 euros, which is a good bit better than here. And similarly for the other 2 indexes. So they're starting off at a better base when we have more information to go on. So it's just to highlight the impact of collaboration at an international level, and the sharing of genotypes and the impact that has from an evaluation perspective. And look, this is just an indication of our 2021 Gene Ireland Angus bull panel. So you can see there's 3 different countries represented here. We have Australia, we've CMX from Canada, we have actually Czech Republic, we have Spain, and again Australia again down there at the bottom. So what happens with these bulls is that if they can be bought at a reasonable price, which is there's a limit in the for participation in the panel, we ask for 600 straws. 500 of those get dispatched, and then if the bulls turn out good after, then there's 100 straws available for pedigree breeding at the end of the test period. So the next couple of slides here are really just kind of focusing on the ability to use a genotype to monitor inbreeding and mating advice. So just, for context, what is inbreeding? Inbreeding is just it's a calculation called a coefficient of inbreeding. It's the probability that an offspring receives 2 alleles at what we call a given locus, which is a gene, and they're both from the same ancestor. They're called identical by descent. Okay, and just a couple of examples here. A parent offspring, if you had a progeny born out of a parent offspring relationship, so if it was a sire that was being mated with his own daughter, the resulting calf would be 25% inbred. Okay, 2 half sibs are the equivalent of 12.5% inbred, and progeny first cousins would be about 6.5%. Okay, so there is some literature evidence to suggest once inbreeding level goes over 6.5% or 6.25%, that you start to see inbreeding depression, which is a reduction in the performance of that animal. So in ICBF we have mating advice and sire advice, and basically there's a limit put in there at 6.25%. And it's it is always important to monitor the matings and monitor the populations. But I'm just going to give an indication over here on the right hand side as to the difference between looking at it from a pedigree based inbreeding calculation, which is just using what that's recorded about the sire, the dam, and the previous generation. So you can see then that for Aberdeen-Angus at the moment, the level of inbreeding is well below the 6.25%. Okay, so it jumps up and down a little bit, but you can see that the genomic inbreeding is slightly different. It's slightly more elevated, and it's going along similar trend lines. But one of the reasons maybe here is that with pedigree-based recording, we have incomplete pedigree, okay? Whereas with genomics, we kind of have the full picture there about the relatedness between 2 different animals. So we would tend to look at both in combination and make decisions based on let's say what goes into sire advice. We're building a new module there where it looks also at the genomic relationship matrix to make sure that that's also below that 6.25%, because you will get some cases where a pedigree-based inbreeding coefficient is underestimated relative to a genomic-based inbreeding coefficient. So this one here then is just on a similar I suppose concept, and what I've just done is looked at all the artificial insemination sires that have been used in Angus sires that have been used in Ireland over the last maybe 20 years, and looked at the relationship between the pedigree coefficient and the genomic coefficient. Okay, and if there was no difference, they'd all be on a straight line all the way up. They'd all be sitting on that black line. But just to highlight, some of the couple of the kind of key, I suppose, groups here. So this is one where the pedigree-based relationship matrix is indicating almost as a 0% relationship between 2 Angus sires. But when you look at the genotypes, you can see that there's a big range there. Some of them are also down at indicating there's very little relationship there, but some of them go up as far as indicating that they could potentially be full sibs or be a parent offspring. So, and these are all males, so that would be a a sire and a progeny. Both are that are AI sires, are indicating that they're up near 50% related. The second group here is this kind of cloud here, and these are indicators of half sib relationships. So on average, they would have 25% in common based on a pedigree relationship. So all these animals up along here, based on pedigree relationship metrics, you're indicating that they're 25% related. Whereas you can see with the genomic relationship, it does manage to filter out. So you have animals down there as low as 7 or 8%, up to as high as 50 or 60%. And obviously that's a more, it gives more information there to suggest that you could have two half sibs in there, and some of them are almost as related as full sibs, and others are almost as unrelated as the rest of the population. And finally, this group here, then, it's there would be sire-son relationships, indicating that they're 50%. But you can see again the genomic relationship there. It's starting to separate them out into more information, so you can actually, very useful from a breeding point of view, in that if you wanted to take two sons to go into AI, you may look to make sure that they have as least they're as least related as possible within that full sib range. So again, it's just to highlight what you can do with the data. And finally, here on this graph here, we've just plotted all those sires on the left, as many of them as possible, to indicate the average relationship that they have had with the Angus cow population in Ireland over a period of time. And you can see it's going from 2004 up to the current day. And you can see some of these sires here that are indicated here in red, they were heavily used in the population, and they were quite heavily related to the cows of a particular time period. Okay, so even up to a relationship of almost 25% related to the current cow population. But by and large, there's, sires are not used that heavily, so that there's a lot of lower relationship there, less than 5% related to the population. So again, they're useful population metrics that you can glean out of genomics. So the next area just to cover will be traceability and breed composition. So with a genotype, we have the potential to estimate what's the breed composition of that particular animal that the genotype has come from. And basically, to do that, you do need a range of purebred animals in your data set, so that if the industry wanted to create a marked difference here, such as if there was a steak being bought in a supermarket, or an actual animal that's live, that's going through an auction house, wanted to be traded, that you can take look for the genotype. Sorry, I don't know. I think I'm just, anyway, my mouse has deserted me here. I was meant to bring up a little. Oh, there we are. Okay, so you made genotype that steak. It may come up in here in this cloud here, which is really in around the Angus cloud, which separates very differently to some of the other breeds. So you can see there, your Holstein Friesian, they're very much an admixed population, that they do run over one on top of the other. The Hereford down here, quite distinct. Limousin here, Charolais and Simmental and Belgian Blue. So you can see that the Angus is very distinct in the DNA signature, which allows you really to make a very good stab at the breed proportion of that animal. But here it also might be a crossbred animal, so it might be part Angus, part Holstein Friesian, and it'll lie somewhere in the middle of the distribution between the two. So again, that's just another potential benefit from genotyping, that you can actually design traceability around it, and estimate breed composition. So look, I know Katie's going to touch on this one. The genotyping chip that we have, it's a custom chip. I guess it's updated as we know more and more information. I won't go into too much more detail because Katie is actually going to cover that one. Finally, the last point I'm going to touch on in relation to the application of genomics to a breeding program is an initiative that we're working on here now, is a DNA-based calf registration. So if you think about what are the benefits to doing this, basically you'd increase your accuracy across the board. You remove your pedigree errors almost at source. So the whole idea is here is that as soon as the animal is born, herds that have fully genotyped out their cow herds and are all using, let's say, sires that are all genotyped as well, that you can use the information in the database to actually to correct all your pedigree and confirm all your pedigree at source. Okay, so it will help to remove pedigree errors early. It'll also help to increase known parentage levels, because we do have still have a lot of unrecorded sires in the population. If we got all the calves genotyped, we'd actually be able to record by and large be able to get almost full coverage at the sire recorded level. And you get genomic predictions then well ahead of sale. So, you get them, within a couple of months of the animal being born. The other aspect then, other aspects that we see as being positive is that it is easier to probably sample calves versus mature cows. It would also then allow full population screening for major genes, for any lethal recessives that may still yet to be investigated in the population. And it also allows a different mating advice package to be built when you know that every animal is genotyped. Also, in terms of a point of difference in product, you get breed confirmation, but also you get some novel traits we're working on now around genomic breeding values for meat eating quality, which could have a benefit for the rare, the abattoir, and be it the supermarket or a restaurant that's actually able to actually prove that beef has come from a particular source and has a certain genetic merit for meat eating attributes. So just to outline how this process has been piloted, basically when the calf is born, it tends to get tagged with what we call a dual tissue tag. So basically there's one of these as part of a long-running national scheme to eradicate the national population for BVD. So one sample goes off for the BVD testing, the other sample goes off for DNA sampling, where then it returns to the ICBF database and the parentage is confirmed, and any parentage errors get fixed. Okay, and before the cattle passport or the pedigree cert is issued, the parentage is fully confirmed. So it means you don't have to go back and change any of your let's say your documentation related to that particular animal. And just a couple of stats on the evolution of that DNA project. It's now running since 2018. Started off with a modest 18 herds and 1,500 calves, and it's kind of built up now to this year 401 herds and 40,000 calves. And if you look at just the I suppose the metrics over time, we can see that the purple here is 2022, and you can see the other years there that the metrics are getting better over time. So we're managing to turn around 67% of samples now in 14 days versus 32% back in the initial year. And I suppose, look, 93% of animals now we can manage to turn them around within 21 days, which, look, it's getting to the point where it's quite acceptable, particularly for the dairy farmer who wants to move those surplus calves off the farm quite early. And just in the context of where it has taken us, we're seeing about 14% sire errors prevented, about 6% dam errors, but also about 2% sex errors changed at source. So look, in summary, I'd like to say that DNA has many uses. Okay, I think we're only scratching the surface in terms of the full utilization. Currently, we're really leveraging it for parentage verification, discovery, and genomic breeding values. But better utilization does require an integrated database to capture the additional aspects such as traceability, mating advice, major genes. It can only be achieved through collaboration nationally, in terms of the adoption of both genotyping, but also the adoption of indexes, but also internationally through, sharing of breeding values and sharing of phenotype and data going into international evaluations. You get back the, information in those outcross sires, but also maybe in a time, as we move forward, more animals get genotyped, national, international cooperation here, where many partners come together to develop a chip, and that obviously has an implication for the amount of chips that can be ordered and the price can be negotiated then with the big chip manufacturers in order to drive down the cost of genotype, and then everyone benefits from there. So in terms of future opportunities, then we see DNA technologies being useful in the climate mitigation space, which is really hot at the moment. Okay, and that's really in terms of putting a much better basis under the genetic merit of that animal and its ability to, well, I suppose the greenhouse gas that particular animal emits relative to the animal in the next field. We feel that's a big additional technology that a lot of breeding organizations can help to use to make a case for maintaining the current level of output that's there in the beef herd. And finally, then, look, there will be opportunities down the road for customized management depending on the genetic merit that's been derived from that genotype. So look, sorry if I ran over there, Shane, but that kind of was just a quick summary of some of the benefits of genotyping.